actually, no one's. Okay. thesis advisor. It's always hard to know how to introduce a student for a defense because there's so much to say. It all started in my case in the fall of 2011 when I was reading this application from this student from Canada. And it talked about how he had been to CERN and he'd done these great things there, and he was really good at computer science. He's really, all these wonderful things, great letters. I said, we've got to get this student. So we were, enthusiastic about Stefan from the beginning, and he did not disappoint. He's worked on all kinds of things here, starting with sort of Fermi Gamma Ray Space Telescope, dark matter annihilation type of work, more recently going more in the statistics and computer science direction towards transdimensional probabilistic inference. He'll tell you about that today. We've, been many places, went off to a summer school on dark matter at Stanford a few years ago. There are many stories about that. And Julie already told some of them in her thesis defense. Stefan was not seriously injured at that time, which is good. The Fermi Summer School, I don't know, we've been a lot of places. So anyway, I don't want to take any more time out of Stefan's. There'll be more to say later over champagne. Please.
All right. Well, thank you very much for the kind introduction, Doug. And as is tradition here, I'll start out by acknowledging and thanking a lot of the people here that have, made my grad school journey what it is. And I guess one theme of my thesis is, how much information there really is in images and pictures. And so this introduction section is going to be mainly pictorial. Later on, I'm also going to tell you I'm going to make a lot of claims about the completenesses of different catalogs. I will start with this with a disclaimer that the following list is far from complete, but I'll do the best that I can within the next few minutes. But of course, I have to start with my advisor, Douglas Finkbeiner, and here he is comparing his length scale to that of a sequoia. One of a very rare instance where Doug can actually feel short. And Doug's just been a great advisor and mentor these past few years. As he mentioned, he encouraged me to go to a lot of conferences and interact with a lot of different scientists, and encouraged me to go to summer schools to learn about different topics. And also, if you're in a conference in California, you've got to go check out the nature over there. And so he's just taught me a lot about how to do science, and he's always been supportive with, not only the science, but applying for jobs and just, grad school life in general. And perhaps one of the most important things he taught me is how to throw and catch two frisbees at the same time. And maybe this inspired our later work where, maybe you're not sure if it's one frisbee or two frisbees. And I've also had the great pleasure of working with the greater Finkbeiner group, the other grad students and postdocs that he's had, as well as those who are just kind of in our sphere of influence. It seems that hiking in California is mandatory for participation in our research group. But don't worry, we also do a lot of work too. This last semester, Doug took us all out to Cape Cod to have a hack week. And this is an email that I believe he sent his wife with the title, Big Science Happening. Input, chips, cookies, Pop-Tarts, and Mountain Dew, and output science. So this is Josh, Catherine, and I talking about transdimensional inference, which I'll tell you about later. And the whole group of us there were working so hard that we overheated the router, and we needed to give the router an ice pack in order to continue having internet. I'd also like to thank my thesis committee for being here, especially Željko Ivizic, who's just flown in from Seattle. He's at Seattle. I don't know where he's flown in from. And my committee has been instrumental in guiding my research these past couple of years, and I want to thank them for for being here today to give me even more feedback. And I've had the benefit of learning from a lot of the great scientists that we have here at the CFA. One person I'd like to thank in particular is Professor Karin Oberg, who actually graciously agreed to be my godparent to be received into the Catholic Church a couple of years ago. But she's also, a great astrochemist, as everyone here knows. And so she's been not only a spiritual mentor, but also a great professional one as well. And I remember back in 2012, it would have been spring of 2012, when I got the phone call from Doug telling me I got into Harvard. Definitely an exciting phone call. But what really made that decision easy for me is when I came in that spring to visit the department. And this is a picture from the grad student picnic the year that I arrived. And, this is just such a friendly, welcoming, supportive department. And, I could say a lot of things about a lot of the people that are here. But I think just the sense of community that's here is really valuable. And I'd also like to thank our administrators, Rob, Peg, Nina, and Uma, who have helped me out on numerous occasions with all sorts of administrative things, especially, dealing with Canadian money coming in and passports and all that sort of stuff. And I'd like to take some time to thank a few of my closest friends who have really supported me through this journey. And with the Boston Marathon happening yesterday, a lot of people say grad school isn't a sprint, it's a marathon. I think a couple of my friends and I took this a bit too literally. This is Zach and Charles and I at the Manchester City Half Marathon a couple of years ago. Us in front of a Miss Universe teen pageant screen, and then an action shot of the two of them starting the race. But this was only the start. I had to do a half marathon in order to train with Marion to run the Martha's Vineyard full marathon last year. And so, grad school is like a marathon, both figuratively and literally, and these people have run with me, both figuratively and literally. And I was planning to spend the next few minutes going over some really tortured similes, like how grad school is like a song, or grad school is like a roller coaster, or how grad school is like a tropical island. But instead, I'll just leave these pictures up of Kate, Pierre, Fernando, and Philip. And like I said at the beginning, one of the themes of my thesis is that images really do contain a lot of information. So for this slide, I'm just going to leave a selection of pictures up from my time here in grad school. Again, far from a complete list. This is all I could fit on one slide. And finally, I'd like to thank my parents who are sitting here in the front left, who have flown here all the way from Edmonton, their first time visiting here in Boston. And this is them outdoors enjoying camping, not quite in the wilderness, but still, in the outdoors. And, they've always provided their loving support and have always encouraged my interest in science. And, every kid has a dinosaur phase, and Alberta is a good place to grow up if you have a dinosaur phase, because you can go to the Drumheller Valley where a lot of the dinosaur bones are actually dug up. Then, of course, I had an astronomy phase, and here's my mom and I at the Dominion Radio Astrophysical Observatory in Penticton, BC. And it appears I just never quite got out of the astronomy phase, but my parents have been okay with that and have just been there for me every step of the way. And so, with that, as we say in Canada, allons-y, let's get on to the science. And I'm here today to talk to you about my thesis work in developing probabilistic cataloging for crowded fields. And I'll unpack that a bit more later in the talk. But first, I want to start out by speaking a little bit about the history of astronomy and how the practice of astronomy has always been entangled with making catalogs of objects we can see in the sky. And to start off, I'll start with this picture of the night sky, which I don't know if might be a bit washed out to the audience here, but I'll roll with it. And here, this is a picture taken from the Okanagan Valley in British Columbia. And hopefully you can see here the Big Dipper, in obvious asterism of 7 stars if you see it in the night sky. And, the first astronomers, I would say, are the ancient cultures that named the stars and placed them into constellations and then used these stars and constellations to keep track of the seasons and to navigate around. By counting and naming the stars and keeping track of their positions, they made a list of stars that they then used for useful purposes to keep track of the year or to navigate. But even before the invention of the telescope, there's a lot that you can do with just naming the stars and keeping track of them. Hipparchus is credited as the first to find the precession of the equinoxes, which we now understand to be the axis of rotation of the Earth spinning around, like how the axis of a top can spin around in a circle when you spin it. And this is, back in ancient Greece. The Almagest by Ptolemy, Ptolemy's catalog remained relevant up until the time of about Tycho Brahe and Johannes Kepler. Brahe was famous for making really exquisite measurements, again, without the aid of a telescope. And Kepler was able to use these measurements to actually demonstrate that Mars had to have an elliptical orbit, providing very strong support for the sun being at the center of the solar system rather than the Earth. So, of course, the invention of the telescope was important to astronomy, but soon after the invention of the telescope was the advent of photography. And photography changed how astronomy was practiced, because now you don't need to sit there with a notebook while you look at the sky. Instead, you can take a picture of the night sky through your telescope and have a permanent record of your observation. Here, I'm showing a plate from the Harvard Glass Plate collection of the Andromeda Galaxy and some of its neighbors. And with this permanent record, you can make much more meticulous measurements than you could if you were just sitting there with a notebook without a picture. And if you're the director of the Harvard Observatory around 1900, you hire the women computers, made famous by David Sobel's latest book, to analyze your photos for you. And you can see here that one of the computers has gone through and identified different stars and galaxies in this image that they wanted to measure. And this is really the start of what we think of as the modern astronomical survey, just taking pictures of the sky and identifying what we can see. I would argue that the next kind of revolution in astronomy was the advent of digital technologies, both digital cameras and computers. With this combination of technology, you could now do something like the Sloan Digital Sky Survey, where you have a computer drive your telescope around and take digital images, like this one on the left. And you could also write a software pipeline that looks at this digital image and identifies all of the stars and galaxies automatically and gives you a catalog, a list of all the stars and galaxies that are identified, as well as their positions and brightnesses. And so now cataloging is really an algorithmic endeavor. It's really in the realm of applied math and computer science. And if you ask a lot of astronomers about what they think of when they think of the Sloan Digital Sky Survey, a lot of them might think of the catalog first, the list of objects that these surveys found and identified. But in some sense, these surveys are fundamentally collections of images of the night sky. And we use different software algorithms to turn these images into catalogs, into lists of objects. And the reason we do this is because we have all sorts of scientific questions, but those questions aren't, what is the brightness of this pixel? What is the color of this pixel? We have questions about the brightnesses and colors of stars and galaxies. And a catalog allows us to answer these questions. If you're Daniel Eisenstein, you might look at the correlation of different galaxies on the sky and find the baryon acoustic oscillation. Or other people have looked for new dwarf galaxies by looking for overdensities of stars that were previously unidentified. Or you could look at the brightnesses and colors of the stars in a globular cluster and learn about that cluster's chemical composition and its star formation history. And I mean, this is just a tiny slice of what astronomers do with catalogs. a lot of astronomy is really this second arrow in going from astronomical catalogs to questions of scientific interest. But I'm actually here today to talk to you about this first arrow, this first step in going from a set of astronomical images to a catalog. And I'll tell you about the sorts of issues that can come up in this step, and also what some possible solutions might be. So the rest of my talk will be divided into 3 parts. In the first part, I'll introduce some of the issues that can come up when you try to catalog crowded fields, then introduce what probabilistic cataloging is and why we should think about using it. Then in the second part, comprising the bulk of my thesis research, I'll show you an application of probabilistic cataloging to a globular cluster called M2. And this is a very crowded stellar field that I'll show you an image of. And in the final part of my talk, I'll speak about the work that I'm currently doing in trying to make probabilistic cataloging a more feasible software pipeline so that we can use it in future surveys like LSST. So I'll talk about the sorts of computational improvements that we've made, and also how we can add galaxies in addition to stars in our probabilistic catalogs. So in the first part of the talk, to introduce some of the statistical concepts that we'll be talking about, I'll use this coin to talk to you about the likelihood. And so this is a loonie, what Canadians call a $1 coin, because it has a loon on one side and the queen on the other side. And imagine I flip this loonie 20 times, and I get the curious result that it keeps coming up tails, and I flip it 20 times, and it comes up tails each time. The question that immediately comes to mind is the coin rigged? It really seems like the coin must be rigged. Well, the statistical concept of the likelihood can help us understand what's going on. So we can talk about the likelihood of getting 20 tails in the row, but we have to assume some model of reality. So first, let's assume this coin is fair. Let's give it the benefit of the doubt. If the coin is fair, we can repeat that experiment of flipping it 20 times, and we'll get all sorts of different results. We might get 12 tails or 8 tails, all sorts of different numbers. The likelihood of 20 tails is, if you repeated this experiment, the fraction of the time that you would get 20 tails in a row. And as you can tell, that's going to be a very small fraction if the coin is fair, because you have a 1/2 chance of getting a tail each time you flip the coin. So you have to take 1/2 to the 20th power, because we're flipping it 20 times in a row. And this turns out to be about a 1 in a million chance, vanishingly small. But the likelihood depends on how we've modeled reality. What if we make a different assumption about the coin? What if we assume that the coin is somehow weighted to always come up tails? Then, if we flip the coin 20 times, the only possible outcome we can get is 20 tails in a row. So the likelihood of getting 20 tails in a row with a rigged coin is 1, or 100%. And the main thing I want to convey about the likelihood is that you make different models of reality, and the models of reality that have a higher likelihood are better fits to your observations. They better explain what you're observing, and so you're more likely to believe them, which is why if you flipped a coin 20 times in a row and got all tails, you would assume that the coin was unfair. So what does this have to do with stars and cataloging? On the left-hand side, I've made a fake image of a star, and here I'm using the convention that more ink actually means more light. So you're looking at a bright spot, even though you're looking at a dark spot on the slide. So this is, some image of a star that I've made up. And it turns out if you look at the same star with the same telescope under all the same conditions, you actually won't get the same image each time, because there are various sources of noise that come into play. So if we looked at the same star a bunch of different times, we would get all sorts of different images, as the noise would change each time. And just like when you flip a coin 20 times and you get different outcomes each time, the same thing happens when you observe a star. So let's say we wanted to measure the position and brightness of this star. First, we would have to look at this image and decide that there is a star there. Let's assume that's easy. We'll come back to that. Let's make a guess for the position and brightness of the star. And this is now our model of reality. we can then make what's called a model image, which is the image you would get of this star if there were no sources of noise at all. By comparing this model image to the real image, you get, if you subtract the model image from the real image, you get residuals. And these residuals are important because if you do a calculation on the residuals, you'll actually get this likelihood. And this likelihood is assuming Gaussian noise, for those of you who are familiar with that concept. But the idea is you make a model, you compare it to the real observations, and decide what the likelihood is. And you can then modify your model. Let's say, okay, this likelihood isn't good enough. I can move this star over, calculate a new model image, and calculate new residuals, and then decide that these residuals are smaller than the ones I had before, and thus this model has a higher likelihood. And so again, this concept comes up that we can change our model to have the maximum likelihood, and this is going to be the best fit for our image. And so these are important concepts that come to play when we catalog images like this one from SDSS, where you can clearly see individual galaxies and stars. You can decide they're there. You can measure each one individually. And everything, current software that we have works spectacularly in this regime. But I'm here today to talk about images like this one of M2, the globular cluster that I was talking about earlier. And as you can see, there's a lot of stars in this image. The brightest ones you can identify individually, sure. But as you look at fainter and fainter stars, they almost look like they start to blend together. Astronomers call this blended or crowded image. And I'll show you the sorts of issues that can come up when you try to look at an image like this one. So here is a very small patch of that image, a 10 by 10 pixel patch. And again, darker pixels have more light in them. And let's say we wanted to try to catalog the stars in this part of the image. Well, there's at least 3 stars, 3 blobs that we can identify. And let's start with the most obvious one down here. And maybe we pick a maximum likelihood position for it, a best fit position in flux. All right, let's move on to the second most obvious one, this one. But one thing that you realize is if you actually want to maximize the likelihood of our 2-star model, you have to move the first star over a bit. The best fit for the second star is going to affect what the best fit is for the first star. And so what we've learned is that sources or stars that are neighboring each other are covariant with each other. What you decide for one is going to affect how you measure the second one. And of course, this problem gets even worse as you add more stars in. If there's a third one, you've got to push the first 2 around. But let's say, we've got computers and stuff. We can deal with this part. One annoying thing about crowded fields is, like I said, the faint stars start to look like they're all blended together. So you can't be sure how to deblend the image, you can't be sure how many stars are even in the image in the first place. And let's say we were unsure about whether, maybe these 2 additional stars exist. You might be content to say, okay, these stars are faint. It's okay if I lose them as long as I measure the brightest stars. All right. But the problem is the measurements that you make for the bright 3 stars depend on whether or not you decide these 2 faint stars exist. If you decide that they actually exist, then the maximum likelihood actually forces you to push the other 3 stars around. And so not only are sources covariant with their neighbors, they're covariant with how you decide to deblend the image. They're covariant with what sources you decide have even existed, which is a very strange covariance to think about. Now, it's true that a globular cluster is a very extreme example of a crowded field. Not a lot of the sky looks like a globular cluster. But we're making new telescopes like LSST that are much more sensitive than previous telescopes that we've built. But they're on the ground, meaning that their angular resolution is limited by Earth's atmosphere. And so by making a more sensitive telescope with a comparable angular resolution, we're going to be detecting more stars and galaxies in the same area of sky. And we're actually going to be making our images more crowded by making our telescopes better. And so thinking about how we can actually analyze these crowded images is going to be important as LSST comes online. So now that I've told you a bit about the issues that come up in cataloging a crowded field, I'll introduce probabilistic cataloging. But first, I want to introduce the idea of Bayesian inference. And my friend the loony is going to come out again. And I have a different question this time. What if I flip it just twice? And I get tails and another tails. Is the coin rigged? And intuitively, the answer is I haven't flipped it enough times. I don't know whether or not it's rigged. But what if we look at the likelihood of getting two tails? The likelihood of getting two tails with a fair coin is 1/2 times 1/2, or 1/4. Whereas if I assume the coin is rigged, then two tails is the only outcome I can get, so the likelihood is 100%. But it seems like there's something missing here. I've only flipped the coin twice, and yet the likelihood for a rigged coin is 4 times the likelihood for a fair coin. But it seems wrong to say that it's 4 times more likely that this coin is rigged than fair. That's clearly a wrong statement. So what's going on? One way we can look at this problem is through the lens of Bayesian inference, where probability is not only just the frequency with which things occur, but also your degree of belief in different models of reality. And Bayesians talk about a prior and a posterior. A prior is your degree of belief about different models before you make some set of observations. And the posterior is your degree of belief after you make observations. And you get the posterior by combining the prior and the likelihood. So what does this look like in the case of our coin? So let's say, there's nothing particularly special about this coin. Maybe it's, it was in the change that I got the last time I went to Tim Hortons in Toronto. And I don't think my cashier is involved in a gambling ring or anything, so I have no reason to believe that this coin is rigged. Maybe I think there's a 1 in 1,000 chance that this coin is rigged. And this is a statement about my degree of belief in that this coin is rigged. So I'm not very suspicious of this coin, maybe 1 in 1,000. But after I flip it twice and get tails both times, I can then combine this prior with the two likelihoods that I calculated for a fair coin and a rigged coin. And now my posterior degree of belief that this coin is rigged is 1 in 250. So I'm still not suspicious of this coin. This coin is probably fair. But I'm slightly more suspicious of it now than I was at the beginning. And if I kept on flipping it and kept getting tails, this posterior would keep on growing. A nice feature of Bayesian inference is that you don't need to choose a single model of reality to believe. You can instead just state your relative degrees of belief in them. Like this statement that I think there's a 1 in 250 chance that the coin is rigged. The rest of the time I think it's fair. And you could calculate this posterior for every single possible model of reality, but that is computationally expensive in a lot of scientific cases where there's a lot of parameters that we want to play with. So instead, generally, people think about this posterior as a distribution over different models. And this distribution is something you can sample from to get an ensemble of possible models. In the case of this coin, if I were to sample the posterior in this case 250 times, I might get 249 models where the coin is fair and 1 model where the coin is rigged to show my level of suspicion about it. And I'll also give a 1-slide crash course in Markov chain Monte Carlo, which is a technique that's often used in Bayesian inference to sample the posterior and give you this ensemble of models. So let's move on from the coin case and imagine that there's just 2 different parameters that we're fitting, represented by x and y in this slide. And this blue blob in the middle is the place where the posterior, this is the combination of parameters where the posterior is highest. And now I want to get a sampling from this posterior. In Markov chain Monte Carlo, and specifically Metropolis Hastings, you can start in a random place in this parameter space and then make proposals, make jumps as to new places you want to go. If your proposal takes you closer to the center of the posterior, you always accept that proposal. If it takes you away, you sometimes reject it and you sometimes accept it. The farther away the lower the posterior gets after your proposal, the more likely you are to reject that move. And it turns out if you do this over and over again, and you use a computer for this, because I'm not doing this by hand, you can mathematically show that you'll get a sampling from the posterior. This collection of locations that you've made follows the posterior distribution that you wanted to sample. So Doug and I built off of work done by Brewer, Foreman, Mackey, and Hogg, who applied this idea of Bayesian inference to the process of cataloging itself, what we call probabilistic cataloging. And the interesting conclusion that you get is that instead of inferring one catalog from an image, you should infer an ensemble of catalogs, a sampling from the posterior distribution. And this helps us handle deblending ambiguities because we've got an ensemble of catalogs, and no one tells us that each catalog has to have the same number of stars. If we're unsure about whether there's 3 or 4 or 5 stars in an image, we can put those each in different catalogs in the ensemble and actually take account of that uncertainty that we have. This ensemble of catalogs also gives you the covariance between different sources. You can see how if one source moves to the left, maybe its neighbor moves to the right. And you can see that by looking at kind of different frames of this ensemble. The one feature that might be unusual to those of you who are familiar with Bayesian inference is that this space of possible catalogs is actually transdimensional. What that means is because we're allowing each catalog to have a different number of sources, each catalog has a different number of parameters, which is something that's not usually done in Bayesian inference. But it turns out there's actually a rigorous mathematical framework that you can use to handle the fact that the space is transdimensional. For the benefit of those of you who are familiar with MCMC methods, I'll show you one slide on how that works. And I'll do that by comparing it to the Metropolis-Hastings algorithm. And so whenever you make a proposal, you have to calculate an acceptance ratio, the probability that you're going to accept that proposal or not. And you get that by comparing the posterior at the place that you're proposing to go to and comparing that to the posterior of the place that you already are. And here I've broken up the posterior into the prior in brown and the likelihood in blue. And the nice thing about the Metropolis algorithm specifically is if your proposals are symmetric, you're just as likely to undo the move that you did as you were to make the original move in the first place. The acceptance ratio for the backwards move is just the reciprocal of the acceptance ratio for the forward move. One framework that you can use to deal with transdimensional spaces is called Reversible Jump Monte Carlo, presented by Green in his 1995 paper. And this framework allows you to make proposals that change the number of parameters. One such proposal might be to add a new star to your catalog, what I might call a birth move. And a couple of interesting features come out. First, you need to have a prior on how many sources you think are in the image. You need to decide how much less likely n+1 sources are as compared to n sources. Not something you usually have to do. Also, you have to decide how you're going to add new stars to your catalog. And that's represented by this expression Q at the bottom here. You have to decide what positions and brightnesses you're going to give new stars when you put them into your catalog. And that gets compared to the prior that you have on your stars. Reversible jump is so called because for every transdimensional move, you have to have a reverse move that undoes it. In this case, that would be a death move that removes a star from a catalog. And just like in Metropolis, the acceptance ratio is the reciprocal of the forward move. But this gives you the interesting feature that this Q still shows up, and this Q is telling you how to add stars. And what this is telling us is that you can't define birth or death in isolation. They really come as a pair of proposals, because once you need to decide how you're adding stars in order to calculate the acceptance ratio that you need to remove them. So now that I've given you a short overview of how probabilistic cataloging works, I'll show you an application of it to this to a part of this image of M2. And this work is the first time that a probabilistic catalog has been made on real optical data. And to my knowledge, it's the largest such probabilistic catalog to be made, containing about 1,000 sources, which is tiny by modern cataloging standards, but kind of the cutting edge for this technique. One reason we looked at M2 is that it's been observed many times by many different telescopes, but particularly by the Sloan Digital Sky Survey, whose data I will actually be using, but also by the Hubble Space Telescope. Hubble has the advantage of being above Earth's atmosphere, and so it has a much clearer view of the globular cluster. To show you how much of a clearer view, I'll bring back that 10 pixel by 10 pixel image that I showed you earlier, and I'll show you the same part of the globular cluster as observed by Hubble. And you might not even believe me that this is the same part of the sky, but it is. And you can see that Hubble just has a much better view of what's going on. And we're going to use Hubble data as a comparison. We're going to use Hubble as a gold standard or a ground truth to compare against. And we're only using it for comparison. The Hubble data is not being folded in to the catalog I'm about to make. So if we look at that 10 by 10 pixel patch, a team from the Sloan Digital Sky Survey cataloged this image using a standard software pipeline called DAOPHOT, actually made by a guy in Victoria, BC, Canada, so that's kind of cool. And that pipeline identified 3 stars in this part of the image that I've marked with blue crosses here. And anytime you see crosses or X's, the size of the symbol corresponds with the brightness of that star. If you remember what our Hubble image looked like, well, if I plot the Hubble stars on top of this image, you can see that the DAOPHOT catalog is having some problems. There are a lot more than 3 stars in this image. And even worse, the 3 stars that it reports are actually combinations of real stars that Hubble is able to observe. So you're going to get the wrong brightnesses and colors for these 3 stars. But it might just be the case that, like, why are we using Sloan to look at this really crowded globular cluster? We have 10 by 10 pixels. That's not very much information to work with. But we tried applying probabilistic cataloging to this part of the sky, and here's what we got. In red is the results from probabilistic cataloging, or I might call it PCAT from now on. And you can tell that it's a lot closer to the Hubble catalog. And as I said before, probabilistic cataloging doesn't only give you a single catalog, it gives you an ensemble of catalogs that I'll now show you in this animation. Each frame in this animation is a different catalog drawn from this ensemble. And you can see the covariance between sources as they appear to push each other around. And you can also see here in the lower lower right corner, there's a star that pops in and out of existence every so often because the fit is unsure as to whether or not that star exists. But even with that uncertainty, it's taking that into account. It's when measuring the neighboring stars, it's accounting for the fact that this source may or may not exist. So this animation looks very nice, but we can also look at more quantitative metrics, like the completeness of our catalog of PCAT versus the completeness of DAOPHOT. And it's apparent that PCAT is able to better deblend these images, better find the stars. And by doing so, it goes over a magnitude deeper into the image. For the non-astronomers in the audience, that's about 2.5 times fainter into the image. PCAT can find stars that are about 2.5 times more faint than the stars identified by DAOPHOT, which is a huge win because we're using the exact same image. The information that you needed to identify these stars was in the image all along. We just needed a technique that was able to dig that information out to make full use of it. But completeness is meaningless without also looking at the false discovery rate. And at least brighter than 20th magnitude, PCAT makes fewer false discoveries than DAOPHOT does. At the fainter end, there are some issues going on. One such issue is that I only allowed PCAT to put in stars that were brighter than about 22.5 magnitude. But Hubble found a bunch of stars that are maybe about 23rd magnitude, and they sometimes came in pairs. And so PCAT wasn't allowed to put a 23rd magnitude star down, but it could put a 22nd magnitude star down. And putting a 22nd magnitude star in the image was better for the likelihood than putting nothing at all. So it was trying to fit the image as best as it could, but that counts as a false discovery against it. I also have some reason to believe that there's a limit to what you can actually do with the Sloan image, and we actually might be coming up against this fundamental limit. We can't get around the fact that it is a crowded image, it is going to be hard to find stars, and at some point it might actually be impossible to find fainter stars. If we look at that animation that I showed you, and instead of looking at the frames, stacked all of the frames into one image, this is starting to look more like a normal catalog with individual sources that you can identify and even kind of uncertainty clouds or uncertainty contours around each of them. And so we actually came up with a procedure that can summarize the probabilistic catalog into something that looks more like a normal catalog. And you lose the covariance between sources. You don't see them pushing each other around anymore. But the uncertainty bars that you get on the sources take account of that covariance. In the Bayesian language, these errors have been marginalized over what neighboring sources are doing. And you can use this mostly like a normal catalog, except in cases like the lower right-hand star, it only appeared in 41% of the catalog samples, and so you can see it annotated with that detail there. And it turns out that this condensed catalog acts pretty much the same as the whole ensemble of catalogs. If you look at the completeness, the red and purple lines almost lie on top of each other, which is what we want. And they also perform similarly in terms of the false discovery rate. Another thing that this condensed catalog allows you to do is it allows you to identify stars that are more or less contaminated by their neighbors. One metric that we came up with is called the degradation factor, which is the uncertainty in flux that's reported in the condensed catalog compared to the uncertainty in flux that you would expect for the same star sitting by itself with no neighbors. And so the best degradation factor a star could have is 1, which is what you want. But you can see here in this plot that we're looking at such a crowded field that a lot of the stars have degradation factors of over 8. Their error bars are being inflated by a factor of 8, which is huge. And there are a lot of applications where you might not want to use these stars in your scientific application. But you can also see there's still quite a few stars whose degradation factor is between 1 and 2, and maybe those would be okay to use. So now that I've shown you a bit about what probabilistic cataloging can do in a crowded stellar field, I'll talk a bit about what I'm working on now and what I'm looking forward to in the future with PCAT. This image is an image from the Hypers Prime Cam, which is really a pathfinder for LSST. And you can see there's a lot more galaxies here than in the Sloan Digital Sky Survey image. And we're starting to approach the point where a lot of these galaxies and stars are overlapping with each other. And it's a current, it's a current open question as to how we can best catalog these images. The main disadvantage of PCAT right now is that it's very computationally expensive. But we're working on ways to make it more efficient. And one way we can do so is to think about the sorts of transdimensional proposals that we do. So we started out with just birth and death. But let's say we looked at a blob of light in the sky and we were unsure about whether it was 1 star or 2 stars. If we wanted to change 1 star into 2, we would have to first move the first star over and then make a second star to recover that leftover flux that we left behind. And this is inefficient because these are 2 separate proposals. And Markov chain Monte Carlo makes proposal choices completely randomly. And so there's no guarantee that we're going to get these 2 proposals in the right order in order to split this star. And conversely, if you want to merge these 2 stars together, you have to undo what you just did by removing a star and then moving the surviving star over. So one way to make PCAT more efficient is to say, maybe splitting a star into two and merging it back into one is something that we want to do very often. So let's make an explicit split move where we choose a star at random and split it into two while conserving the total flux, or the total brightness, and the center of flux. And let's use some kick distribution to make sure that those two stars don't go too far apart. So now this is a single proposal that can be done instead of waiting for two random proposals to line up. Because of reversible jump, we have to have a converse move for the split move, which is a merge that acts on pairs of stars. And we can even weight the different pairs of stars in order to favor pairs of stars that are close together that we might actually want to merge. And again, we want to do the same thing, but in reverse. We want to merge the stars together while conserving the total brightness and the center of flux. We also have started looking at how you might add galaxies to this framework. And really, you can add anything that can be parameterized. And there's standard parameterizations of galaxies, like the Sursich profile. But it's important to keep in mind that this is, at best, an approximation for a lot of galaxies. You're not going to be fitting the spiral arms of Andromeda with this equation. You're not going to fit the tidal tails between two interacting galaxies with this equation. But you might remember from that previous image, there are a lot of galaxies that are only a few pixels wide in this image. And this equation might be good enough to fit those small but numerous galaxies. But when you add galaxies, you have to think again about the transdimensional proposals that you have. So I talked about birth and death and split and merge for stars. You probably also want birth and death for galaxies. And you might confuse a star with a small galaxy or vice versa. So you might want moves that change between those two cases. We probably also want to split and merge galaxies. But do we want to split galaxies into other galaxies or other pairs of objects? One final thing that I'll talk about is that you might remember from before that to calculate the likelihood, we have to calculate the model image. And this is really the most expensive part of PCAT, even when we were doing just stars. But this is going to be more expensive for galaxies, which are more complex. We came up with some ways to speed up our model image calculation for point sources, that is for stars. So we decided, why not take advantage of this fast point source evaluation by representing galaxies as grids of stars. And I guess in reality, galaxies are actually collections of stars, but not in grids like this. And one cool thing about this method is if you want to change the size or orientation of your galaxy, you can just stretch and rotate this grid, and that's easy to do with linear algebra. So let me show you what the current state of the code is, what it can do with both stars and galaxies. And I'll walk you through what's going on in this slide. On the left-hand side, I've got a mock image, an image that I just made up. And because I made it up, I know what the truth is. I know that there's a star in the lower right-hand corner, represented by a cross, and that there's 3 galaxies, represented by these Ys with ellipses around them. The sizes of the crosses and Ys represent the brightnesses of those objects, and the size and shape of the ellipse around the galaxies represents the size and shape of that galaxy. The red symbol that you see there is PCAT starting with a completely random catalog. And as I play the animation, you'll see PCAT getting closer and closer to the right answer. And on the right-hand side are the residuals, the comparison between the current PCAT model and the real image. And right now, the residuals are really bad because I'm literally starting with a random catalog. But let's see how things play out. You can see that right away, PCAT has figured out that there's at least 3 objects here, and it's playing around with their sizes and shapes and maybe even whether or not they're galaxies. But pay attention to these 2 objects in the middle here. There's a big bright galaxy and a smaller faint galaxy, but PCAT is only putting 1 galaxy there, and it's putting down an elongated galaxy because it wants to try to fit the light that's coming from those 2 objects. But it doesn't know yet that there's 2 objects there. But if we give it a bit more time, It looks stuck, but it isn't. Now it looks confused. But it's getting closer to the right answer. Now it's got it. One thing you'll notice is that this lower galaxy is both faint and small, meaning it's hard to tell it apart from a star because of the point spread function of the telescope. And you can see it playing around with both possibilities. Sometimes it thinks that object is a star, and sometimes it thinks that object is a galaxy. And maybe that's the best that we can do with the limited information that's in this image. So now I've caught you up on where PCAT is now. So this is my concluding slide. And I started out by telling you about the sorts of issues that can come up when you catalog crowded images. The fact that you might not even be sure how many stars there are in that image. You might have deblending ambiguities. And also that neighboring stars are covariant with each other and even covariant with their neighbors, which may or may not exist. I then introduced Bayesianism and the idea of probabilistic cataloging, where you infer an ensemble of catalogs. And this ensemble of catalogs allows you to better handle these crowded field issues. By applying it to real data from the Sloan Digital Sky Survey and the Globular Cluster M2, I showed that PCAT is able to perform better in crowded fields, going over a magnitude deeper than DAOPHOT. I've also shown you what I'm working on now in terms of making the code faster and also extending it so that it can apply to both stars and galaxies. And I think that this problem of how to catalog crowded images is going to be, it's just going to grow in importance as we build better telescopes. And I think that probabilistic cataloging is definitely an interesting way to approach the problem. If we can make it faster and also coupled with improvements in computer hardware, this might be the way to go. But at the very least, this might if this is not the way to go, it'll at least teach us about what a crowded field pipeline should look like. So with that, I'll take any questions.
Thank you for a crystal clear talk on a difficult topic. My prior is there's a high likelihood of questions. Lots of questions. Please.
Oh, great talk, Stefan. I guess one question that came to mind was PCAT actually does worse for very faint things. And with these really cool applications you have in mind, how can you set constraints for different problems on when you should sort of have a cutoff in terms of the magnitude?
So that's a great question. And one thing that I'll point out first is that PCAT is getting worse as you go to faint sources. But DAOPHOT isn't even trying at that rate. But even with that in mind, so I'll only give, this is a very cursory overview of this plot, but the point is, in studying just the one star case, throwing PCAT at mock images with just one star on them, we've come up with this idea of a critical flux, above which PCAT is likelihood dominated, and below which it's prior dominated. And you really don't want to believe PCAT in the prior dominated region. You can totally believe it in the likelihood dominated region, and in between you might want to be careful. But it actually turns out, at least in the uncrowded case, you can calculate this critical flux easily. And I'm working right now on how we might be able to calculate this in the crowded field limit as well.
You should pick your own.
Okay. June?
This is really awesome. I was curious about the second arrow. So, so how do you envision for the people who are doing, taking the catalog to doing the science, like how to go about using a probabilistic catalog in the future?
So there's a great question, and I think there's a couple of different ways this could work. Kind of the zeroth order thing is this condensed catalog that we produce is pretty much like a traditional catalog that astronomers are used to. So you can use that and still reap a lot of the benefits. Another way to use the catalogs is to use the ensemble by, let's say you have some, I don't know, cluster finding algorithm or something that you want to run on a catalog. If you have enough computer time to repeat that on each of the catalogs in the ensemble, that'll give you an ensemble of answers, which is actually the right thing to do if you're thinking in a Bayesian way. Pierre?
So it's a public talk, so I don't feel bad asking this question. But have you considered uses of this algorithm beyond astronomy? I can think of many government agencies who would get access to this.
So I haven't thought in detail about applications of outside astronomy yet. I know that Doug's had some interest from the medical field. I guess one thing I would be cautious about is astronomy is, at least stars are nice because they are literally point sources to our telescope. So it's easy to make the model image, whereas if, I don't know, you wanted to find cancer tumors, like tumors aren't point sources, they're some weird blob shape. But that's not to say that the ideas I've developed can't find, can't find other applications. Anna?
So recently some pipelines have started reproducing galaxies as a mixture of Gaussians. So I was just wondering, how does that approach compare to what you're doing with like the grid of point sources?
So that's a good question, and I haven't been able to compare yet. That is a comparison I'd like to do. One advantage that my approach might have, this is an untested statement, is that if your point spread function is not easily written as a sum of Gaussians, this approach can use any point spread function. It can have whatever features you want, and it'll still give you the right answer. But that being said, I think the approach of writing both the PSF and the galaxy as sums of Gaussians is a really clever one. And I know when they implemented that change, they got a lot of performance improvement.
This is really great. Have you tried to apply to multi-band simulations?
Yeah, so in fact, sitting beside you is Richard Feder, an undergrad who's worked with Doug and I on extending this to multiband images. And by fitting the images simultaneously, you can get a lot of information out of them. Sometimes people fit each image separately, but in this framework, you really want to fit them together. You do have to be careful about the PSFs in each band and also making sure that you line up the astronomy in each band correctly, but Richard's done a lot of good work advancing that.
You mentioned this seductive idea that maybe you're actually getting close to the maximum information the SDSS images hold. Is there any theoretical way to estimate that? Like, in quantum mechanics, you can divide space up into little grid cells and figure out kind of what is the maximum, phase space volume associated. Like, is there any theory way where you can just say, this is the kind of maximum upper bound on what's in the image?
I'd imagine so. So I've picked up my statistics on the street, so to speak. I'm not a stat student, I'm an astronomy student. But I do think kind of the next thing I want to do beyond this is I want to jump from the 1-star theory case to the 2-star theory case. But I think there should be a way to quantify how much information is actually in the image. But I don't know precisely what that looks like. But it would be a good benchmark to compare against.
I was wondering if what you're doing is only taking into account the image per se, and not other factors that would be associated with stellar bodies, gravity and 3-dimension and all that sort of thing.
So I guess there's all sorts of things you could expect a catalog to do. And kind of the simplifying assumption that I've made in this catalog is that the stars are pretty much staying still and have the same brightness. But stars actually move, they actually have variability. But as long as you can parameterize those somehow, like the next approximation you can make is the stars are moving in straight lines. You could add that into this framework. If you had like multiple images taken at different times, you could actually try to fit for moving stars, which is something that I might try to think about in my next position, actually.
I'm trying to estimate in my head by what factor you are away from applying this to LSST. So if you take our crowded region in LSST, it's about 10 to the 9 harder problem than your 100 by 100 pixel. We will have 100,000 cores at our disposal, and there are about 10,000 hours in a year. So if we give ourselves 1 year to do it, basically it comes to 1 hour per 100 by 100 pixels. So the question is, how many hours does it take now to you and PCAT to process on one core 100 by 100 pixels?
So it turns out the answer is actually half an hour. But that comes with a caveat. So the Galaxy part of the code is still very untested, like still in early development. But to give you some idea of the 100 by 100 fields that I've been testing it on, I've been testing it on fields like the left. And so you can get usable results with one core in about half an hour. But there's also some like details that come up with Galaxies that I'd be happy to talk about in the private defense. Zach?
Following up on the idea of searching for motion, is it in some sense the case that a very noisy catalog acts like a crowded catalog if you were, say, doing a motion search for things like near-Earth asteroids, like they're looking at with NEOWISE? And could you imagine applying this to basically treat that noisy field as a sort of crowded field, but more than half of the sources are fake because they're just noise, because the asteroids or near-Earth objects kind of moving through it?
So are you saying they're crowded because you'll have like fake detections because of noise peaks and stuff?
I think so.
I'm not sure that they would be crowded in the same sense, but I guess what's traditionally done to look for moving objects is you take two images at different times and you subtract them and look for what moved. And this actually works really well even as you get to moderately crowded fields, but at least the impression that I got, I'm not a moving object expert, but the impression that I got from talking to people at University of Washington is that as you get closer to the galactic plane, this becomes harder to do, and so they're interested in new ideas for how to look for objects. Anna?
Yeah,
Last question.
I have like a very last kind of question. So you modestly said that this might not be the answer for LSST, but to me it sounds like it's really the only game in town. So I wanted to kind of, is there anything else that even comes close to what you're doing?
So I know that the LSST people are working on their software pipeline for making for cataloging those telescope images, but they also have said so they're testing it out on HyperSuprime Cam, and one of the papers literally says deblending is like the foremost problem that we have. And I guess the reason I reserved my statements a little bit is I do think, at least in the Bayesian point of view, this is the right thing to do with all capital letters. The question is, like, right now it's still pretty expensive, but I think this or some approximation of this is what we want to do.
Can I make a follow-on comment to that? So if you have a generative model that actually describes the data correctly, this nails it, right? And it's just a question of speeding up. But the problem we've always had with galaxy photometry is there is no model that can describe all galaxies. And so that's a problem we're not really addressing here. Give us the model and we know exactly what to do, but we don't have that model yet. So that you don't need, the younger students don't need to fear that photometry will be solved by next year. There's still lots of work to do on this. And if you're interested, come talk to me. I'll be looking for another student. So thank you so much. The private drilling will be